PageRank. So the topic for today is PageRank. So the things that we will cover is what is PageRank, why do we need it, what we use it for. We will look at some examples with some random surfers or random walkers on the web. And we will see a very simple example of the web with three websites that link to each other in different ways. And show the matrix for these websites, and then we will look at some ways that people can trick search engines to modify the PageRank for specific pages. And we will look at some special cases of the way pages link to each other that have dead ends and that cause what's called a spider trap. So what is a PageRank? The idea of PageRank is to assign a rank to the page according to its importance. So the idea is that if a page is important, then people will visit that page a lot. So we cannot tell though who is visiting which page at what time. So the idea is to assume that people visit pages at random times. So if that's the case, then we will think of the users of the web as random surfers or random walkers. So the random walker can start at a page at any time and follow random links out of this page. And the PageRank is, we will compute a probability of being at a particular page, but that the way we compute that is in a recursive fashion until we reach the limit or converge. So we will see an example of how we do that. So we have a recursive equation, and so the pages that are important link, or the pages that are important have other important pages linked to them. So a page can be considered important or has a high rank if other important pages are pointing to it or have links to it. If we are to compute this, the importance itself is a vector, because this vector shows which other pages are linking or pointing to our page, and that's eigenvector of transition matrix of the web. And by this matrix, we're showing which page links to which page at any time. And we will see an example of what we mean by eigenvector of the transition matrix. So we will assume that we number the pages, just give them a number 1, 2, 3 through n. And if we have a matrix, then the page I corresponds to the row of the matrix, and the column. So let's say we have a matrix of pages. They are listed both on the left and on the top, and so row I and column I is showing the place for page, for a specific page in the matrix. What is recorded in the matrix is, so the matrix is M, and at index ij of the matrix we have some number, and that number is 1 over the the number of pages that our page is pointing to. So 1 over n if page j links to n pages, including the page itself. So we have 1 over n. This is a 0 if the page j does not link to the page I. So this place in a matrix is essentially the probability that we're likely to visit the page I at any particular time. So if more pages are pointing to it, we are more likely to visit this page at any particular time. So that is what the matrix shows. So it's 1 over n if page j links to n pages, including the page itself. And it's 0 if the j does not link to the page. So suppose that we have a page j, and the page j links to 3 pages. So then for j we will have 1 over 3 because the j links to 3 pages. It links to I, so I is included in that. So at the index ij we have 1 over 3 because j links to 3 pages including I. At the index xj we have a 0 because j does not link to x. So if we have a vector, and each item in the vector shows a probability that some random walker or surfer of the web will land at our page, which is page I that we're considering. So if this web surfer is truly surfing the web by random and clicks on random links, then we could calculate probability that the surfer will land at the ith page and the page I, and that is by multiplying the matrix that we have seen earlier with this vector. So this is the vector of the probabilities for each page. Let's see an example about how this matrix looks like. This vector really if we start by random, we could just pick some random numbers in the vector. We could pick all ones. And if we multiply this vector by the matrix, and we can keep recursively multiplying the vector by the matrix, we will eventually converge or come to the limit to where the numbers don't change anymore. So this PageRank is an iterative algorithm. And so once we keep multiplying like this, the pages that are important will get a proportion of these numbers to how likely a web surfer is likely to visit these pages. So this eigenvector that we talked about, that's once we keep multiplying the matrix with the chosen vector, and that could start with all ones, and when it eventually converges, it's going to give us what's called the principal eigenvector, and that is what is used for ranking the pages. M has each column summing to 1 because remember what's recorded in the matrix is 1 over n. So n is the number of pages that link to it, and we assume that the total sum of pages is 1, so it will sum up to 1. So once we obtain this limiting eigenvector, then it will, once this is the limit of the multiplication, then it will satisfy this equation m times d. Let's see an example. So we cannot show the entire web on this PowerPoint slide because the web has trillions of web pages right now. But what we can show is the web that we see in 1839. There were only 3 websites, and this is how the web looked like. We have Yahoo website, Amazon website, and Microsoft website. This is the matrix M that we were describing. If this, we give example with page I, a location I of the matrix, we have Yahoo right now. And the fraction is 1 over 2 because we said it is 1 over the number of links to that page, including the page itself linking to itself. So Yahoo is linking to itself with this loop. That's one page linking to Yahoo, and another one is that Amazon is linking to Yahoo. So there are 2 pages linking to Yahoo, so it's 1 over 2. If we look at Amazon, let's say Amazon with itself, Amazon does not have this loop here. Amazon does not link to itself, so Amazon with Amazon is 0. If we look at Amazon and Microsoft, so Microsoft has a 1 link to it that comes from Amazon. So there is 1 here. It's not divided by anything because Microsoft only has 1 link linking to it. If you had 2 or 3, it would be 1 over 2 or 3. And so this is what this matrix is showing. This is a matrix for that graph of the web. There is no the distribution. There's not a Gaussian distribution. There's no Gaussian distribution for the web, so we cannot solve by this kind of elimination. But what we can do is iterative solution. Is what I mentioned earlier. We can keep multiplying our matrix by this probability vector until we converge, as long as our vector contains non-zero values, and we can start with a vector that is all ones. So we start with a u equal to 1, 1, 1, 1. And what this means, it is showing the importance of each page. So a 1 for each page represents the fact that each page is of equal importance. We could start with 1 over n. That is what we have in the matrix. But just for our example, we will start with all ones, and what we will do is repeatedly multiply the matrix with this vector and see how the numbers will change. So allowing this importance of the page to flow in the similar fashion as the surfers are randomly surfing the web. If we do that, we will eventually come to a convergence to where the numbers will no longer change if we keep multiplying like that. So let's look at our example with the Yahoo, Amazon, and Microsoft. So what happens is we have equations that we're trying to solve. For Yahoo, the equation will be y/2, because we had two pages that link to Yahoo, and then Amazon over 2, because there are two pages that link to Amazon. Now this equation is for Yahoo. For Amazon, we have it gets Yahoo over 2, so half of its importance comes from Yahoo and 1 unit from Microsoft, and that's because Microsoft has only one link and it links to Amazon. Yahoo has two links, one of them links to Amazon. That's why it gets 1/2 of its importance from Yahoo and 1 whole unit from Microsoft. And Microsoft gets a 1/2 unit of importance from Amazon because Amazon has two links and only one of them points to Microsoft. So to solve these equations, we will use a vector starting all once, and we will multiply this vector with the matrix. So we're just going to replace to solve the equations. We will replace y with 1, so it will be 1/2, a with 1, so it will be 1/2, and m with 1, so this will be 1. So once we do that, then and first equation becomes y is equal to 1/2 plus 1/2, so that's equal to 1. Then the next equation becomes a is equal to 1 over 2 1/2 plus 1, that is 3/2. And the next equation becomes m is equal to 1 over 2, that's 1 over 2. Next, what we're going to do is take these values now and solve the equations with these values. So y will be 1, so 1/2. A will be 3/3, 3 over 2. 3 over 2 divided by 2. M will be 1/2. So here will be 1/2 with 1/2. A is 3 over 2 divided by 2. And this is what we get. Next, we use these values in the equations. And we will keep doing this until the values don't change anymore, and this is when we stop. And so that's when this converges. These are the final values, and if we replace them, we will see that they satisfy the equation. If we have these random walkers, let's see how this works with the random walkers. Each of the 3 websites have the same number of random walkers on their website at this moment. Yahoo has the green ones. There's 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Green ones are at the Yahoo right now. The red ones are Amazon website, and the blue ones are that Microsoft website. They all start with equal number of random walkers. If we are to follow the links, what happens is that because Yahoo has a link to Amazon and a link to itself, so half of the walkers are likely to get to Amazon. So you can see half of the green guys got here. Microsoft, the only place that it points to is Amazon. So some of the guys from Microsoft went to Amazon and then they went to Yahoo. Well, let's see. The Microsoft had the blue ones. Okay, so all of the, because Microsoft only has one link, all of the Microsoft guys are likely to only follow that link. And so they will end up at Amazon. So you can see all the blue ones went over here. The Microsoft got the red guys because there is one link to it from Amazon, and Amazon had the red guys. Half of them, because Amazon has 2 links. So half went here and half went follow the other link. If we are to just follow this probability, and if we continue to do that, we will get some more mixed up. Until we reach the limit. And when we reach the limit, what happens is that it corresponds to our equations that we have seen, to the numbers that solved our equations earlier, is that Yahoo and Amazon had the same importance, which was 6/5, and Microsoft had a lower importance that was 3/5 when we solved our equations, so as that Microsoft gets a smaller proportion of the visitors, the random web surfers, walkers. And Yahoo and Amazon have a bigger proportion, but they're equal to each other.